All right, so last time we talked about what an empirical formula is and how to determine an empirical formula if you have the molecular formula. Today we're going to be calculating the empirical formula from experimental data. And so this is what oftentimes happens in laboratory settings when someone makes a new compound. They're not sure what they made. They think they know what they made. Part of the step is figuring out what the formula is, and then figuring out how that formula is put together physically. And so this is some real-life chemistry that you're going to be doing here, the mathematical aspects of the laboratory data. And so there are three little steps, and there's a little rhyme that you can do to kind of figure this stuff out. And so if you just remember this, mass to moles, divide by small, times to whole. That is a nice little rhyme that gives you the steps to solve these empirical formula problems. Mass to moles, divide by small, times to whole. Okay? And so we're just going to do some examples. So a compound is found to be made of 5.86 grams of nitrogen and 13.39 grams of oxygen. What is the empirical formula of this compound? Okay, and so the little rhyme says mass to moles. And so let's convert our masses into moles. And so we have 5.86 grams of nitrogen, and we have 13.39 grams of oxygen, and we need to convert those mass into moles. Now, you have done single-step problems previous, and so this should not be a difficulty for you. So 5.86 grams of nitrogen, stick it over 1 if you want to, times our fraction bar, and we're going to convert the mass into moles. Well, we have mass here on top, so we're going to put mass here on bottom, and to convert mass into moles, you're going to use the 1 mole equals the molar mass conversion. And so we're going to put 1 mole of nitrogen on top, and we're going to put the mass of the nitrogen on the bottom, 14.007 grams of nitrogen. Divide the 5.86 by the 14.007, and you get 0.418 moles of nitrogen. Okay, then we do the oxygen as well, 13.39 grams of oxygen, and we'll do the same thing. We'll convert it into moles. So 1 mole of oxygen has a mass of 15.999 grams of oxygen, and when you divide 13.39 by 15.999, you get 0.837, 0.837 moles of oxygen. Okay, so that's mass to moles, step 1. Now after step 1, mass to moles, you do divide by small. So you got two numbers over here. You got 0.418 and you got 0.837. Divide by the small one, which is 0.418. So divide both of these by 0.418. When you divide these out by 0.418, 0.418 divided by 0.418 is obviously 1 in. 0.837 divided by 0.418 gives you 2. Now it may not give you exactly 2, but it's pretty doggone close to 2. Actually, let me put the calculator in here and figure out exactly what it gives you. It gives you 2.002, which is 2. Okay, so what does this tell us? Well, this tells us that we have, for every 1 nitrogen, we have 2 oxygens. And so our empirical formula is N1, we don't have to write 1s, O2. That's our empirical formula of this compound. Now, what about the times to whole? Well, right here in this step, what do we have right here? We have whole numbers already. And so we don't need to times to whole because they're already whole numbers. 2.002, that's 2. We're going to be looking for whole numbers in this step. If they're not a whole number, they're going to be a simple fraction. And we'll talk about that in a second when we get to one that works like that. All right, so let's look at the next problem. A compound is 43.38% sodium, 11.33% carbon, and 45.29% oxygen. Determine the empirical formula of this compound. So first step is mass to moles. Let's go and find our masses of these elements on the periodic table. So we have sodium, which is right here. we have oxygen right there, and we have carbon, which is right here. So sodium, carbon, and oxygen. So sodium's 20.990, carbon 12.011, oxygen 15.999. Hopefully some of these numbers are starting to stick in your head at this point. If not, they'll come later. Okay, and so the sodium mass was 22.990, the carbon mass was 12.011, and the oxygen's mass is 15.999. All right, so let's do the moles to mass conversion. Mass to moles conversion. Now, here's the problem. We have percentages here. How do we convert percent into mass? We're going to make an assumption. We're going to make an assumption that we have 100 grams of this compound. Now, if we have 100 grams of it, and it's 11.33% carbon, how many grams of carbon we would have? Well, if it's 100 grams and it's 11.33%, then you're going to have 11.33 grams. So you can very simply just convert the percent signs into grams and you have mass. And then you convert your mass to moles in this step. So let's do that. We have 43.38 grams of sodium. We have 11.33 grams of carbon, and we have 45.29 grams of oxygen. Now we're going to convert all of these into moles by using the 1 mole equals the molar mass conversion. So we'll stick the 1 mole of sodium on top, the 1 mole of carbon on top, the 1 mole of oxygen on top, and on our bottom we're going to put the molar mass of sodium, the molar mass of carbon, the molar mass of oxygen. Found out sodium is 22.990 off the periodic table, so 22.990 grams. Carbon, 12.011 grams, and oxygen, 15.999 grams. So the grams are going to cancel out, leaving you moles. Okay, if you punch these three numbers into your calculator, you're going to get 1.909 on the sodium. You're going to get 0.9433 on the carbon. You're going to get 2.831 on the oxygen. So we have converted grams to moles. These are all moles. I'm going to, for space sake, I'm not going to write out the unit here, but this is moles of sodium, moles of carbon, moles of oxygen. So next step, mass to moles, divide by small. So which one of these is the smallest? That's going to be the 0.9433. So let's divide them all by 0.9433. And when you divide them by 0.9433, you're going to get 2, 1, and 3. And again, this 2 and that 3 may not be exactly 2, but it's going to be really, really close, like 1.98 or 1.99 or 3.01 or something like that. But it's pretty much a whole number. We're looking for whole numbers. That's what we want in this step. If we have whole numbers, then we're good. If not, we have to do step 3, which is times to a whole. But we have whole numbers here, so we're okay. So this tells us that we have 2 what? Well, we started out as what? 2 sodiums. We have 1 carbon, and we have 3 oxygens. So our formula is Na2CO3. And that should look familiar to you. You should be able to name that compound. This is sodium. And what is the CO3? That's carbonate. So that's the formula based on that data. Okay, we'll do one more example. A compound is 52.93% aluminum and 47.07% oxygen. Calculate its empirical formula. So let's go to the periodic table and let's find the aluminum and the oxygen. So aluminum is right here and oxygen's right there. And so 26.982 for aluminum, 15.999 for oxygen. Okay, so back to this page, we got 26.982 was our aluminum mass, oxygen, 15.999, mass of oxygen. So let's do our steps, mass to moles. So again, we have percentages here. Again, that's okay because we're going to assume we have 100 grams. And if we have 100 grams and 52% is aluminum, then we have 52.93 grams of aluminum. So write that down, 52.93 grams aluminum. Convert that into moles, mass to moles. So 1 mole of aluminum has a molar mass off the table of 26.982 grams aluminum. Grams will cancel grams. That's going to give you 1.962. And then the oxygen is 47.07. Convert that into mass. So 1 mole of oxygen, 15.999 grams of oxygen, which cancels the grams of oxygen over there. That gives you 2.942. Okay. Now we're going to divide by small. The smaller one of these is the 1.962, so divide both of these by 1.962. And that is going to give you obviously a 1 here. And here what it gives you is 1.5. It actually gives you like 1.499, but that's okay because it's going to round to 1.5. So here, again, we're looking for whole numbers here. We don't have whole numbers. So now comes in the next step, times till whole. What can we times 1.5 by to get it to be a whole number? Well, 0.5 is equivalent to 1/2. So if we multiply 1/2 by the denominator 2, then that becomes 2 halves, which is 1. So you're going to multiply by whatever is the denominator of the fractional decimal. So we're going to multiply both of these by 2. So times 2 there and times 2 here, and that gives you 2 and 3. And so our formula is Al2O3. Now, how do we know what to multiply by? What are we going to get in this step here where if we need to times by whole, we're going to times by whole? So what we're looking for here is, I'm going to go ahead and erase all this. What we're looking for here are simple fractions. That's what we're going to be working with, are simple fractions. Most likely you're going to get 1/2 or 1/3 or 2/3. These are going to be probably 90+% of the possibilities you're going to get these. So if you get 0.5, for example, that's 1/2. If you get a 0.5 or a 0.49 or a 0.51 or even a 0.52 or 0.48, then just round to 0.5 and then you're going to multiply everything by 2 because that's going to be the denominator you get rid of. The 1/3, you'll get something like 0.32, or you might get a 0.34 or a 0.33. For 2/3, you'll get like the 0.65 or 0.68. Those are going to round to basically 0.66, which is your simple fraction 2/3. So for all of these, you're going to multiply by the denominator, which is 3. Multiply by 3, you'll get a whole number off of those. So when you work your problems out, if you get these simple fractions, then that's what you'll do. On a more rare occasion, you may get a quarter, 1/4, 2/4, which reverts back to 1/2, or 3/4. So you're getting something right around 0.25 or 0.75. So you might get a 0.74 or a 0.27 or a 0.76. For those, you're going to multiply by 4 to get rid of to times till whole. You'll multiply by 4. And so, but most likely you're going to be multiplying by either a 2 or a 3, on a more rare occasion maybe a 4 on our problems. So that's your times till whole step. Okay, so that's it. We'll see you tomorrow.